Hello, I'm Larry Veilleux. I'm a solutions architect and lead the training and consulting services for automotive cybersecurity at SAC. I hope that you enjoy this presentation I put together on electronic vehicle or EV charging. During this presentation, I will cover the four main topics in the order they are listed here. And know that training is a repetitive and stepwise process. Overall, the content and curriculum should have the appropriate level of detail, presented at the appropriate time, and be organized so that the flow of information leads to better comprehension, not drinking from a fire hose. Well, let's see how well I accomplished that here. There are numerous types of vehicle propulsion systems. Many of those came into fruition due to the need for cleaner vehicle emissions, or even no emissions at all. Each of them have many different abbreviations, and some might even be misleading. Relative to this presentation, the types of cars and their corresponding propulsion systems are highlighted in turquoise here. It's interesting to note that electronic vehicles, EVs, actually preceded internal combustion engine vehicles, or ICE, even before the turn of the 20th century. Now let's take a further look into some of the most common propulsion systems, especially as they are related to EVs. Keep in mind that automotive relates to self-propelled automotive vehicles or machines, not just cars. So this applies to different vehicle types, including cars, trucks, trains, aircraft, spacecraft, etc. Although my focus is on cars here, now I'm homing in on the vehicle propulsion systems that are mostly related to EV charging. I mentioned ICE cars previously, so let's move on from that. EVs, electronic vehicles, can apply to many flavors of propulsion systems that are also listed here. As I just mentioned, the vehicle is not just a car, rather it could be a bus or train for that matter. So a pure EV could refer to a bus running off overhead electric wires that is connected to externally and not off-the-shelf internal batteries. Typically, though, when one refers to an EV, they are referring to a vehicle, most often a car, that drives on electrical energy stored in an onboard battery. Which is specifically referred to as a BEV, or battery electric vehicle, that is plugged into an external socket to charge. For the sake of time, I'm not going to discuss hybrid vehicles here. Generally, EV charging is described as three levels. By the way, talking in generalities is somewhat misleading when it comes to EVs and such, just as different propulsion systems or even vehicles in general can be misleading, so can the different charging technologies. First, differentiate between charging at home or even at the office versus charging on the road. Level 1 and level 2 charging is done from one of your AC alternating current circuits at home. Level 1 uses your standard 128 volt shared circuit that you might even plug your toaster into. Whereas level 2 uses a dedicated 240 volt circuit similar to your electric range or clothes dryer. As such, level 2 provides more power, kilowatts or kW, and therefore shorter charging times. Note that with EV charging tech, a kilowatt or kW refers to how much power a charger, supply equipment, can deliver, as well as how much power the onboard charger in your EV can accept. Relative to level 1 charging, using the formula P equals I times E, or pi, 120 volts times 12 amps equals 1,200 watts or 1.2 kilowatts, kW. More on electricity tech later. Destination charging is functionality equivalent to level 2 charging, but rather it is done on the road, such as at a hotel or campground overnight. Well, both level 1 and level 2 charging should be thought of as taking place overnight due to the longer charging times, whereas level 3 charging decreases the charging time significantly to perhaps just 20 or 60 minutes, by both delivering DC direct current charging directly and at much higher voltages, such as 400 or 1,000 volts listed here, This is done at special charging stations, which Tesla has dubbed as superchargers. Note that you would not do DC supercharging at home since one, your electric company would not deliver that type of service to your house. And two, at home, you can afford the time to charge using AC overnight. And honestly, dealing with those higher voltages levels is much more dangerous for the average person. Speaking of charging levels, I have depicted a few of the common chargers for those here, such as a mobile connector kept in your car for level 1 or level 2 charging away from home, a permanent home wall connector for level 2 charging, and a couple of pictures depicting supercharging equipment that you might find at a public charging station. I'm sure that by now the Tesla supercharger looks familiar. Question, why would you not need a home wall connector for level 1 charging? Or why would you? Speaking of charging connectors, I have depicted a few of the common ones here. There are three common types depending on first, if you own a Tesla, and besides that, if your car was built for distribution in the Americas or not. Japan even has its own type of connector, but it's not depicted here. Tesla's connector and charging technology is far more advanced and efficient than the rest. As such, it has a very small, light, and sturdy form factor for both AC and DC charging than the rest do. As such, it is now in the process of being adopted as the North American Charging Standard, or NACS, which will also support adapters to be used by the rest. CCS stands for Combined Charging System, and combo refers to the possibility of being used for both AC and DC charging. Well, something that's inherent to Tesla NACS connectors already. CCS Combo 1, which is used in North America, includes an AC connector on top and a DC connector on bottom. Note that both are required for DC charging since communication with the charging station is still done through the top half, although pure AC charging is accomplished with only the top half, as depicted in the side-by-side pictures in the bottom middle here. You could extrapolate something similar for CCS Combo 2 for usage outside the Americas, and a picture of the combo versus AC only version are pictured at the bottom right. Note that in either case, these are the plugs delivered as either a combo or not, whereas the receptacle on the car will almost always be combo capable, meaning the car itself supports both AC and DC charging. The electric vehicle supply equipment, or EVSE, is either a home AC or supercharger DC delivery mechanism. It is often referred to as just the EV charger. This plugs into the car, as just discussed. The car has an onboard charger, or OBC, which accepts AC or DC voltage. Note that Tesla cars have a different process for accepting DC current, hence the combo connector is inherently built into the smaller footprint. But as mentioned before, Tesla is special in that it just bypasses the OBDC for direct DC charging. Hence, its NACS connector is combo by design. One of the biggest engineering challenges, or call it marvels, is how each manufacturer manages the charging process electronically. There are trade-offs between battery technologies and the capacities and how they respond to the charging process, especially in terms of voltage, amps, current, and corresponding heat that is generated. This results in a unique charging curve that is well documented for each model. The idea is to optimize the charging curve so it charges at or as close to peak power for the longest amount of time. The charging curve, though, is such that as time goes on and the more heat is generated, the charging time increases dramatically, meaning the power curve decreases accordingly. I'll talk about how the biggest improvement can be made by increasing the battery voltage, but this is also a costly choice. In terms of charging stations, there are a number of players today, including Blink Charging, Charge Hub, Charge Point, and Electrify America, or EA, to name a few. Each maps their stations using a user-friendly mobile app as depicted here for EA. Each station describes the number of chargers, charger power, the higher the power, theoretically the faster the charge, and availability of each charging unit. Many even include the rates or costs. Since this map only depicts a single company's charging stations, you can imagine, especially when Tesla is included, there's going to be quite a few, but still a smaller percentage compared to gasoline stations. Another feature of most mobile apps is being able to trace out your route in the most efficient way based on the available charging stations. Obviously, the number one goal is to never run out of charge, but they also consider travel time, the most direct route, and even factor in fatigue. In other words, a trade-off between how long you're driving versus how long you're waiting for your charge. As such, the goal is not necessarily to always top off your charge. I mean, one thing I'll mention here is the most efficient use to prolong the life of your batteries is always to try and only charge to 80% as much as possible. So in this example, which on the left only depicts about the first quarter of the journey, we stop more often for shorter lengths of time, balancing driving time versus waiting to charge time better. Regarding charging time and range tech, I'll compare the Ford Mustang Mach-E to the Lucid Motors Air, the latter being a model of engineering brought to you by former Tesla engineers. Obviously, the first thing that jumps out is range. So one may assume that the Lucid Air has a larger battery pack, which is true, but also the materials and engineering also provides the Lucid Air with more range as well. The Lucid efficiencies also translate to better MPGE or miles per gallon equivalent, but not necessarily kilowatt hours or kWh. Note that MPGE or miles per gallon of gasoline equivalent is a measure of the average distance traveled per unit of energy consumed. So if this were an ICE car, how would its MPG be rated? And think of kilowatt hours as the electric equivalent to gallons of gasoline. A gas car has a fuel tank that can store a certain number of gallons of gas, and an EV has a battery that can store a certain number of kilowatt hours, or kWh. So with combustion cars, we measure their efficiency in miles per gallon. With EVs, we use miles per kilowatt hour. These are the types of things that we use to compare not only makes, but also models. I mean, honestly, it's a bit confusing and difficult to cover in any detail in a short amount of time. Finally, notice the difference in the power source being 400 versus 800 volts. I made mention of that relative to charging times earlier. I will also address that a little deeper when I discuss electricity technical details next. The window sticker is a label required in the United States to be displayed in all new automobiles. It includes the listing of certain official information about the car. We're used to seeing it for traditional ICE vehicles. Here, at least, is the EPA's fuel economy portion of the label for the 2011 Nissan Leaf EV. One thing that I did not mention on the previous slide, which you may have noticed and thought it was quite strange, is the fact that EVs actually get better city versus highway mileage. It seems strange until you realize that with an EV, highway driving is a constant drain on the battery, whereas city driving takes advantage of regenerative braking to replenish the batteries from time to time. Okay, here we go with the electricity technical details. Well, there are three main factors: voltage, amperes, and watts. I mentioned voltage in regards to the levels of charging earlier. Besides AC versus DC, note that voltage is the amount of force of the electricity, which at home is either 120 or 240 volts. Here, the international system or SI of units is depicted first, followed by the conventional or common signal. Therefore, voltage is represented as either V or E. Amperes is the volume or current of electricity, which for 120 volts is typically 15 to 20 amps. Amperes is represented as either an A or an I. Watts equates to the power generated by the electricity. or work that is being done, or even heat being generated, such as a 100-watt light bulb generating light and giving off heat. Watts is represented as either a W or a P. To tie these three together, the question that came up on the previous slide is, well, if a typical light bulb is rated at 100 watts, or P, and a typical circuit is 120 volts, or E, then how many amps, or I, would it draw? To answer this, we use the conventional symbol references to formulate the expression of pi, which is easy to remember, or P equals I times E, meaning power equals current times force. So to calculate current from knowing power and force, we divide both sides of the equation by force or volts and end up with I equals P divided by E. Or for this example, I equals 100 watts divided by 120 volts, which is 0.93 amps. But why am I covering these basics of electric current theory? Well, even though the Lucid Air has a much greater battery capacity, it can charge in about the same time as a Mustang Mach-E. How is that, though? As I mentioned earlier, current generates heat, and heat is highly regulated by the EV, especially during the charging process. This has a direct effect on the charging curve and therefore the charging time. Since I equals P divided by E, the higher the E, or voltage, V, the less current, heat, is generated. And the Lucid has an 800 volt power source versus the Mach-E's 400 volt. Therefore, the more efficient the Lucid's charging curve will be, just due to physics. Just another Lucid Motors advantage. Well, thank you for taking the time to view this presentation. Feel free to reach out to me if you have any questions.